Hello, everyone. I hope you're doing well. I'm very glad to welcome you to the second day of our conference dedicated to our dearest Sabir M. Gusein-Zade. And I'm very glad to announce the first speaker for today. It's Maxim Eduardovich Kazarian from Higher School of Economics and the Skoltech University, who's going to talk about XY swap duality in topological recursion. Maxim Eduardovich, the floor is yours.
Thank you. It's really a great pleasure for me and honor to take part in this conference and deliver a talk. My congratulations to Sabir. The subject of my talk is not directly related to singularity theory, but I will show that my experience in singularity theory helped a lot in solving the problems that I will be discussing. This is our joint project with a group of our team. There are 5 of us, and in the last years there are about 10 preprints and related topics. And I will. So my approximate intention is as follows. I will introduce the language of endpoint functions. And then I will use this language in different aspects of the relationship with KP theory, topological recursion, and XSwap duality that enters the subject of the title of my talk. Also, it's formulated in terms of endpoint functions. And I will explain the main results, the relationship of this XY swap with topological recursion and KP duality. KP integrability, and show how it works in practice. So it's rather related to the theory of the integrability theory. In the integrability theory, we have a function and the integrability theory. In the integrability theory, we have a function and we impose certain equations, usually ordinary differential equations or partial differential equations on this function. The number of variables is infinite, so it's rather hard to speak about analytical properties of this function, so I consider it as the formal power series. Analytical properties of this function, so I consider it as the formal power series. And in practice, it could be regarded as a generating. The bottom indices could be repeated. So F is just the Taylor coefficient of this expansion. It's a Taylor series, Taylor expansion formula. And we can regard the function as a generating function for the corresponding coefficients. And there is an alternative way to pack the same coefficients into a generating series, so which is called endpoint functions. So in the original series, as Alexander noticed, that the indices ki are used as the indices of the t variables. But here we use the same indices ki as the exponents of z variables. So in the first case, we use the same set of variables for all possible n, but here for different n, set of variables for all possible n, but here for different n, we have different collections of the Taylor coefficients into generating series. So the original potential is replaced by a collection of endpoint functions for different n. So before discussing this correspondence, let me make. So it's interesting that the correspondence. So it's interesting that the integrability properties for the original potential is reformulated in terms of endpoint functions, and this reformulation is quite unexpected. Yeah. Yes, so this is symmetric. So because the Taylor coefficients, the endpoint functions is symmetric.
So even
Yes, yes. The Taylor coefficients are symmetric, of course. Yes, you're right. We assume that this F coefficient symmetric, of course. Yes, you're right. We assume that this F coefficients are symmetric with respect to permutations of the indices.
And in this last formula, indices are in the brackets.
It's just by misprint, yeah. Let me make some two technical corrections of this correspondence. First of all, it's better to consider the differentials rather than functions. So I put the product of dzi. So I consider this as a symmetric product. It's a symmetric differential. This is a symmetric product. It's a symmetric differential form. So it means that it's one form with respect to each of the argument. If the coordinate z is fixed, then this correction doesn't matter. But we will see below that when you apply change of z coordinates, then it's behaves more naturally when it is treated as a one differential rather than argument. It's symmetric and differential. And another technical remark that it's useful. It proves that it's useful to correct this formula by adding by hand a singular term for n equal to 2 with singularity. A singular term for n equal to 2 with singularity on the diagonal. At the moment, it looks not clear why it is we should do that, but this simplifies a lot of formula, and actually there is a deep geometric meaning behind this, but it's not seen for a moment. So let me show how it works. So we would like to reformulate some properties of the original function in terms of endpoint differentials. So let me show how it works. There is a, for instance, differentials. So let me show how it works. There is a, for instance, famous KP integrable hierarchy. It's an infinite, particular infinite system of partial differential equations, quite famous, with constant coefficients, with nonlinear, and there is a rule how to produce other equations of the hierarchy. It's an infinite system of equations. Probably you know there are Hirota-Bar linear equations or commuting flows of pseudo-differential operators and Lac representation, wave functions, and Sato-Grassmannian. There is a huge theory behind the KP hierarchy. But let me reformulate how the KP integrability is reformulated in terms of endpoint functions. It's quite useful, but unfortunately not. It's known to the specialists, but not so popular. So I will popularize it. So it proves out that the function f satisfies equations of KP hierarchy if and only if the corresponding endpoint functions obey so-called determinant identities. It means that there is a unique functions k in just two variables. Sometimes it's called Baker-Achiezer kernel or Séguin kernel, and all differentials are expressed as a kind of determinant, or to be precise, connected determinants of the matrix whose entries is a k of zi zj.
What is determinant with zero upper index? What is determinant with zero upper index?
So the connected determinants means that usually we use the same expression as stations. Here we use only great cycles. Since we use the great cycles, it means that we do not involve diagonal entries. The diagonal entry is not defined because it has singularity on the diagonal. So this is it has singularity on the diagonal. So this is an example. So we have one term for n equal to 2, two terms for n equal to 3, 6 terms for n equal to 4, and so on. So to say dimension, the k is half differential which with respect to each of the argument, but you see in each monomial every variable appears twice, once in the first place and once in the second place. So this monomial, and since with respect to each of the arguments. And since k has singularity on the diagonal, omega 2 also has a singularity on the diagonal. So we cannot avoid singularities on the diagonal. And by the same reason, every summand in this connected determinant has singularities on the diagonals. But it happens that these diagonal singularities cancel out, and the total expression is a regular function in all its arguments. So only omega 2 is singular, and all the higher differentials are regular. So it's really not so obvious that these determinantal identities imply all those partial differential equations. It's not so obvious how to express one in terms of the others.
So if I take k, z1, z2, arbitrary k, z1, z2 of that type, so in construction scenes, it will be a solution of...
Exactly. This is a unique way to parameterize all solutions. This k involves information of the point on the corresponding Sato-Grassmannian and so on. This is the way how to parameterize all the solutions. And this is so k is arbitrary. Actually, in the formulation, k was postulated just existence, but of k. But actually, it could be expressed either in just existence, of k. But actually, it could be expressed either in terms of the potential or in terms of the differential. So it's somehow included in the formulation of the differentials. This equality, you see, holds for n starting from 2. This equality, you see, holds for n starting from 2. For n equal to 1, it's meaningless because k of z is not defined. But if you regularize, after regularization, it's become regular, and you can restrict to the diagonal, and we get omega 1. And actually, omega 1, choice of omega 1 does not affect KP integrability. Change of omega 1 corresponds to the change of linear terms of the potential, and adding linear terms to the potential does not change KP integrability. Implies the following. So in the original setting, we considered endpoint functions as a formal power series. But let's assume that they extend as a global meromorphic objects on a compact Riemann surface. In this case, we say that the potential admits a spectral curve. So we say that potential admits a spectral curve if all the endpoint differentials extend as symmetric global meromorphic differentials on the Cartesian product of some Riemann surface, one and the same for all n. So we have a spectral curve, we have a particular point and a local coordinate z, and if you expand these global meromorphic differentials in terms of this local coordinate z, we recover the original potential. But on the other hand, if the differentials are defined globally, we could take any other local coordinate or even a different point on the spectral curve. So we have a collection of global meromorphic differentials. We can illustrate not just one, but the huge family of potentials. Each corresponds to a specific choice of the expansion point and the local coordinate. And the determinantal identities imply that the KP integrability does not depend on the choice of the local coordinate. It's an internal property of the system of differentials. If KP integrability holds them of differentials, potential corresponding to some choice of Q and Z, then the determinantal identities hold true, then they hold globally. then they hold in the expansion at any point, so the same property holds for any other point of, for the potential associated to any other point. So we, along with this original potential, we have a huge family of potentials, and all of them are solutions of KP hierarchy. Potentials, and all of them are solutions of KP hierarchy. Recursion that produces a solution of KP hierarchy starting from arbitrary algebraic surface. This construction involves also a choice of a point and a local coordinate at this point, if you're familiar with this construction. And it proves out that the dependence on the point and the local coordinate and the Recursion construction exactly is as I described. Recursion construction exactly is as I described. So it means that behind the Recursion construction, there is a globally defined system of n differentials. So in the original formulation of Recursion, it formulated it in terms of corresponding solution of tau functions. But actually, what we have here is just global. They're defined as follows. So we start with a compact Riemann surface. We take the basis of holomorphic differentials. There is a G-dimensional space of holomorphic differentials, so we choose a basis. And our endpoint differentials are expanded as combinations of these monomials, eta k1, eta k2, and so on. Monomials eta k1, eta k2, and so on. And if you choose properly, the coefficients of the corresponding system of differentials will be Kp integrable. And according to Recursion, these coefficients should be chosen as the Taylor coefficients of the logarithm of the theta of the Riemann theta function. So there is a theta function. There is a theta function associated to corresponding Jacobian, and we take the Taylor coefficients of its logarithm. I'm not discussing why this is true, but just the very form, the true object of Recursion construction is not the tau function, but the system of global holomorphic differentials. And again, global holomorphic differentials. And again, we should add some singular correction for n equal to 2, adding a so-called Berg kernel, which is singular on the diagonal. There is another origin where a system of n differentials appears naturally is just the topological recursion, which is the main subject of my talk. So the topological recursion was discovered by Eynard-Orantin and Chekhov in some problem of mathematical physics in matrix integration. And then it proves out that physics in matrix integration. And then it proves out that this procedure of topological recursion solves in a uniform way huge number of enumerative problems in mathematical physics, combinatorics, Gromov-Witten theory, and many other subjects. So but it happened that they are expanded in as a power series in some extra variable h bar. We have so-called topological expansion, and so it's encoded in the two-parameter family. So it's encoded in the two-parameter family omega gn, where g is a non-negative integer and n is positive. Now, each omega gn is meromorphic rather than the whole differential. And so the topological recursion produces this system of differentials in a uniform way, starting from the initial data. Now it's become more and more popular. There are conferences and books and huge number of papers. I counted more than several hundred papers in the archive whose title contains the combination topological recursion. So now it's very popular, but still let me explain how it works. So starting from the initial data, we produce a system of differentials. And from the initial data, we produce a system of differentials. And the enumerative information that we read of the system of differentials are, as usually, the coefficients of the power expansion at some point of the spectral curve. But the idea is that the recursion itself involves global analytic behavior of the differential on the whole spectral curve. Meromorphic is very important for the topological recursion. So let me go to the details.
What is the starting point?
I like your questions because you. I like your questions because you just you just predict the next slide always. So the initial data of topological recursion, which produces all the differentials, is essentially as follows: is a quadruple x sigma x y b. So sigma is a compact Riemann surface, and x and y are two meromorphic functions. We see in the example that sometimes it's useful to admit logarithmic singularities for x and y, so we are actually sufficient to assume that the differentials dx and dy are globally defined and meromorphic. And the whole study is some study of the behavior of the differentials in the neighborhood of the critical points of behavior of the differentials in the neighborhood of the critical points of x, which are zeros of dx. So we take this differential dx, takes all its zeros, and then we assume that all these zeros are simple. So all critical points are of Morse type. And also dy should be holomorphic and non-zero at the critical points of x. This is non-degeneracy condition is assumed. And B is a Bergman kernel if the where Z is an affine coordinate on the CP1. Otherwise, it's fixed by 1. Otherwise, it's fixed by the condition that it has singularity on the diagonal of this kind, and no other singularities, and also this condition defines B up to biholomorphic summand, which is fixed by vanishing A periods. So the
Is it possible to exclude the Bergman kernel from the set of initial data? Is it uniquely determined by the curve?
Thank you, because it's really, I'm happy that your question also predicts my next sentence. So the Bergman kernel indeed is fixed by the Riemann surface and by a choice of AB cycles. But there is an extension of topological recursion to the situation where sigma is not necessarily compact. Then we have more freedom in the choice of B, and that's why I included this to the initial data. However, in this particular setting, you are right, B is fixed by sigma. Thank you. Data are used in the definition of the initial differentials, 0,1 and 0,2 differentials, so-called unstable differentials, and all high differentials, stable differentials, and all high differentials are defined by an inductive procedure that I will review now. So this what kind of objects we obtain as a result of the recursion. These differentials that we are going to construct have the following properties. First of all, they are really globally defined and meromorphic and symmetric. And behind, they have poles. And they have poles. And all these poles are allowed only at the critical points of x, or at zeros of dx, with respect to each of its argument. So if you regard these n differentials as differential in just one of the argument, then all the positions of all poles are fixed. These are zeros of d. Behind that, they have vanishing a periods. And this means that the whole differential could be uniquely recovered from the principal parts of its poles with respect to just any of its arguments. So we consider omega g just any of its arguments. So we consider omega gn as a differential in just z1. If you know position of the poles, if you know principal parts of the poles, and the fact that the a periods are vanishing, then it could be recovered uniquely. There is even explicit residual formula for this. Define omega gn is sufficient to identify the polar part of the singular points. And then we recover the differential by this residual formula. And this is how the recursion works. A recursion has two steps. On the first step, we compute the principal parts of the poles using some condition called loop equations, and then we recover the whole differential globally from the information on the principal part of the poles.
You are saying that this equation allows the left-hand side?
Yeah. So when you compute this residue, you need to know the behavior of this differential just near the pole, right?
If it is given to you,
And so if you add to this any holomorphic summand, the result will be the same. It depends only on the polar part of the differential near the pole. And the left-hand side is global. So now I recall that the loop equations are intended to identify the polar part of the differentials at the singular points, and they claim as follows. We take certain combinations of the differentials, and we impose that these combinations should be the polar part is not necessarily zero, but it should be even with respect to the involution of the critical point is simple. It's a Morse type, so X is locally a degree 2 covering, a ramified covering. It has an involution of deck transformation, and we claim that the polar part of these combinations should be odd with respect to the deck transformation. If you apply the involution, the function is multiplied by -1 plus holomorphic summand. -1 plus holomorphic summand. So the loop equation claims that the polar part of the differentials themselves is even. And the quadratic loop equations mean that this combination also has a polar part which is even with respect to the deck transformation. So the expression, if you look at the expression inside the brackets, the variable z appears appears twice in each monomial, so it's a quadratic differentials with respect to z. Then we divide by dx, it becomes meromorphic one differential, and we impose the condition on the polar part of the differential. So roughly speaking, the first equation determines, says that the even part of the pole of omega gn is vanishing, and the second, the quadratic loop equation, fixes the odd part of the pole. So in each step, we use this, in each step of the recursion, we use these loop equations to identify the polar part of the singularities, and then we apply the projection property, recover the global meromorphic behavior of the corresponding differentials. So this is how the topological recursion works. It's really quite unexpected. So I recall that we are interested, our goal is compute the power expansion of collections. Certain recursive procedure involves analytic extension of this differential at the points behind the convergence radius, because the convergence radius is just bounded by the positions of these singularities. So it's really bounded by the positions of these singularities. So it's really quite strange. But however, it works, and it proves out that there are huge amounts. So these are just example. The Kazarian potential corresponds to the simplest spectral curve with a single critical point of x at the origins, and then there is a enumeration of maps which appears in also in matrix integration. Maps which appears in also in matrix integration. We have the spectral curve which x is a function of degree 2 in D. It has two critical points, and there are more complicated cases. So here you see the Hurwitz numbers, Gromf-Witten invariants, and so on. And these are just a small portion of huge family of examples. There are dozens of examples which solve some particular enumerative problems from different areas of mathematics. It's really miraculous. I don't, yeah.
So let's consider the first example.
Yeah.
So you start with x and y, you construct differentials, and then you take particular point, expand it.
Yeah, here one should take the infinity.
Okay, but after that you will obtain intersection numbers of some particular. So
Yeah, the coefficients. Yeah, the coefficients of the expansions for omega gn are just intersection number of psi classes. Exactly. This is probably one of the most efficient way to compute intersection numbers of psi classes in practice.
if you construct all these multi-differentials.
Yeah, yeah. So I implemented this in computer and used this as a true definition of intersection numbers. So this is a formulation of Witten conjecture.
So in your list, what's the relation between the second example and the third example?
It's you're right. They look similar. The x point is the x function is the same, y function is different, and the expansion points are different. Yeah, they're closely related, but yeah.
What's the potential function of the second example related to the second? Because using the yield relation, you can get the pole function.
Actually, Gromov-Witten theory of CP1 is its potential depends on two indices. The homology of CP1 is two-dimensional. There is a zero-dimensional class and two-dimensional class, and the corresponding underlying cohomological field theory is two-dimensional. So the true potential depends on two sets of times. But in my original definition, we have just one set of times corresponding to the local expansion at some points. So it's also the Grom-Witten potential is also hidden in the system of differentials, but not in so straightforward way as I described by the local expansion. But it's still there is a way to extract the Grom-Witten invariance from this omega gn for this spectral curve. I pass to the main subject of my talk, the XY swap duality. So it deals, we consider the following problem. So we take the original topological recursion and then we swap the role of x and y. From the first glance, this operation looks quite strange. X and y functions in topological recursion is quite different. X function defines the poles of the differentials, the involution of the deck transformation, and so on. And y function is used only in the definition of initial differential omega 0, 1. However, let's do this and just take y as a new x function, x as a new y function. We obtain a new recursion. And there are really examples where this swap is natural. For instance, if enumeration of maps, you can there is a how it's called. You can there is a how it's called the duality. You can replace vertices by faces and faces by vertices and something like that. So there are problems where this swap is natural. However, if you enumerate maps with some fixed valencies of vertices, or enumerate maps with fixed degrees of faces, embedded graphs. So these two problems are related to one another because there is a duality. You can replace faces by vertices and vertices by faces by duality of graphs. And this is more or less corresponds. We do this just formally, exchange the role of x and y. And it proves out that there are explicit combinatorial formulas expressing one family of differentials in terms of another family of differentials. And these relations, these correspondence, these formulas are quite explicit. They're complicated but quite explicit. It looks like it's really very strange because the corresponding topological recursion have quite different analytic properties. The original differentials has poles at the zeros of dx, and the dual differentials have different position of poles and different number of poles. They have poles at the zeros of dy. And this xy swap transformation is organized in such a way that the poles at the zeros of dx cancel out when you pass to the dual differentials, and the dual differentials are holomorphic at the. So here are examples how it works for small gn. So you see the expressions are quite explicit. We take some combinations of the original differentials, then substitute argumental differentials, then substitute arguments in some way, then differentiate, and they obtain the dual differentials. So the formulas are quite explicit. So let me show the definition itself. The definition itself is not so simple. So please, to simplify definitions, I collect the original and the dual differentials in the single genetic series involving the H variable. And so from the original system of differentials omega n, we would like to obtain the dual system of differentials, and as an intermediate step, we introduce some collection of differentials which has twice number of arguments as the original differentials. The omega big is constructed from the original one by some explicit formulas. So constructed from the original one by some explicit formulas. So let me show how they look like. So the formulas are not so nice, but they quite have some experience in KP integrability theory. You would probably recognize some expressions from there, but from the first glance, the expressions are quite messy. We take certain primitives of the original differentials, then combine them in some strange way. Take the exponent and add some singular factor, and then apply the inclusion-exclusion relation. So it's quite complicated. But however, I assure you that this formula, in spite of it reduces to these particular expressions from small gn, and also I implemented on the computer this main formula, and I am able to make computer experiments. So let's skip the details, but just for reference how it looks like. And then from this omega capital, I do the following. This formula should be read from the right to left. I take this omega n capital and then apply this substitution in this omega n capital, and then apply this substitution. Instead of zi, I substitute some series involving some partial order derivative with respect to x. And it involves add one more factor here, also involving some combinations of derivatives of x and y and u variables. And finally, I do the following. I expand the series in u variables and replace any appearance of u series in u variables and replace any appearance of u monomial by the corresponding exponent of the derivative with respect to y variables. So it's not so easy to accept this formula from the first experience, but it's really quite explicit, and it could be implemented. And if you fix g and n, that it involves only finite number of summands. It's very hard to explain the motivation for this definition without explaining the theory of there is some motivation for this definition, but if you just look at this, it looks here, it looks quite messy. However, the formula works, and it's quite explicit transformation starting from the original system of differentials and two functions as x and y. We produce a new system of differentials. And the new system of differentials is also has the same analytic properties. It has singularities on diagonal for n equal to 2, only meromorphic, symmetric, and so on. And the inverse transformation given by the same formula with x and y swapped. And the main statement is that, as I mentioned already, the X-swap transformation is compatible with topological recursion. Transformation is compatible with topological recursion. So let me come back to the examples once again. What does it mean? Omega differential has singularities at zeros of dx. Then we apply at this summand, and it happens that this summand has singularities both at zeros of dx because of these terms and zeros of dy. And it happens that singularities at zeros of dx cancel out, and the singularities of zeros of dy survive. So the dual differential has singularities of only at the zeros of dy. And also, for this differential, it happens the same. And moreover, each particular summand has singularities on the diagonal. But after this particular summand has singularities on the diagonal. But after this, if you apply these combinations, that it happens that all diagonal singularities cancel out. And this result is regular with respect to all three arguments. So this cancellation of unwanted singularities is where I use my experience in singularity theory, and just use some local study of these formulas and show that this cancellation of singularities happens. Okay, so let me show how it works in practice. So if you look at the examples that I presented before, Hurwitz numbers, Gromov-Witten of CP1, enumeration of maps, and Kazarian potential. In all those cases, the spectral curve is rational, CP1, and the y function is just z, or logarithm z. But what's interesting that the y function has no critical points. It means that the dual, the critical points. It means that the dual, the formal XY dual spectral curve data have no critical points. It means that the dual topological recursion is trivial. All the differentials are equal to 0, except the. So we know explicitly the result of topological recursion on the dual side. It's 0. Then we apply the XY swap formulas, and we obtain the expression for the original differentials. So originally, the first way how the topological recursion was applied, people applied honestly the recursion step by step. But it happens in all those cases, the recursion step by step. But it happens in all those cases, there is an explicit closed formula for the result of this topological recursion. So, for instance, this kind of formula exists for Kazarian case, which enumerates enumeration of intersection number of psi classes, enumeration of maps, Hurwitz numbers, and so on. So again, we start with kind of connected determinant, which involves some additional u variables, then add some extra factor, and replace again every appearance of u monomials by the corresponding derivatives with respect to x. This is quite explicit. Yeah, so this formula holds if y is equal to z, but for Gromov-Witten CP1 formula holds if y is equal to z, but for Gromov-Witten CP1 it was logarithm z. Then the differential also has no zeros. The corresponding topological recursion is still trivial, and we have a similar expression. Application of this X-swap duality is as follows. So in the original definition of X-swap, I have to stop. Okay. In the original definition of X-swap duality, we used the fact that the initial data are non-degenerate. But it happened that this non-degeneracy condition for the initial data could be relaxed considerably, and actually removed. And there is a formulation of topological recursion which does not involve the non-degeneracy condition for the initial data. And this is replaced by the following conditions: that when you apply the X-swap transformation, we require that the singularities, and when you apply the inverse transformation, the singularities at the zeros of dy should cancel. And this, it happens that this condition could be, this definition could be applied independently on the non-degeneracy condition for x and y, and this defines the generalized topological recursion, and we have studied this recursion. It has a lot of applications and nice behavior, but this is beyond of my talk. And the last remark, let me skip this. And the last remark that I applied the X-swap transformation for arbitrary system of differentials, independently of any KP integrability of topological recursion, but it proves out that this XY swap transformation preserves KP integrability. And as a corollary, we get the swap transformation preserves KP integrability. And as a corollary, we get that any topological recursion, any differential system of differentials topological recursion on the rational spectral curve is KP integrable. For all those problems that I formulated in the examples, enumeration of Hurwitz numbers, Gromov-Witten potential, Gromov-Witten of CP1, intersection number of psi classes, enumeration of maps, all these corresponding potentials are solutions of KP integrable hierarchy. And this is holds if the spectral curve is rational. If the spectral curve is not rational, this is holds if the spectral curve is rational. If the spectral curve is not rational, but then this exactly does not hold, but there is a modification which also produces KP solutions from topological recursion, but which is related to Kirchhoff construction, but this is some extension of this theory. So let me stop here for a moment. Thank you.
So, Maxim Eduardovich, thank you for a very nice talk. Is there any questions?
May I ask you to be more precise about non-rational spectral curves? Is it true that for any non-rational spectral curves, the resulting system of differentials will not be KP integrable?
Again, I would like to say that we didn't. I didn't ask you to ask this question for me, but however, if the spectral curve is rational, then the topological recursion differentials do not produce KP solutions. But there is a modification which is a kind of mixture of topological recursion and Kirchhoff construction, which produces KP integrable differentials. And for that, we replace the original Bergman kernel in the definition of spectral curve data by a system of differentials called blobs. And if these blobs are KP integrable, then the topological recursion differentials are KP integrable. So this was an old conjecture of Eynard and co-authors, and using XY duality, we were were able to prove this conjecture. So there is a slightly more complicated construction which involves topological recursion on the spectral curves of higher genus. And also, as an input data, we use Krichyver differentials. Then the resulting differentials are not holomorphic anymore, but they have poles at zeros of dx, and they're still KP integrable. Yeah.
Okay, more questions? Comments? Admirations? No? Okay, then so let's thank Maxim Eduardovich again. And I guess we have 5 minutes for